Welcome to week 8, Wednesday of Math 105. We have a quick announcement on the to-do list for this week. I've put in a link to our spreadsheet in the office hour study session time before class. We did a little bit with the spreadsheet. I'm not going to show you now. Let's wait till we naturally get to that in the lecture. But that's now something that's useful this week. So the link is there also. For homework is almost ready. So I took away the red thing that says not ready yet. For A, everything should be good. I put in a little dice chart. All the problems now have multiple choice things you can pick. So no one has turned one in to test it because sometimes my JavaScript is bad and it gives you wrong for a correct answer, but I think it is good. Homework for part B is almost ready, but on problem 9, I need to make a Venn diagram. So most of the homework B is ready. If not, then it will be soon. Remember, if you don't see the updated version, then either refresh your browser cache, or if you can, just a Control F5 for Windows, or whatever it turned out to be. Was it Shift Option R for a Mac? There are ways to do a hard reload and refresh the cache for one page without having to do it for all of them. If you weren't here on Monday, then let's go through this a little bit more carefully. We're doing probability, which we should probably actually call combinatorics, but that's okay. And there is a lot of jargon in this topic. The actual math is not hard. It's just adding and multiplying, and when it gets complicated, the calculator will do things for us. But there's a lot of jargon that makes it difficult to do. So it is especially important that you don't just rely on a lecture, but look at the textbook chapter and look at this week's activity. When you go to the activity, then it has lots of good extra practice, and as always at the bottom of the activity is a link to an answer key, so you can see how you did. So the activities are good things. Paula's weekly worksheet this time is not actually a worksheet. It is just her notes about probability. So that's another good way to look at things explained in a different way to help solidify all of the jargon and vocabulary. There's a lot of optional videos, and this is an easy one to just search the internet and find even more. So if you are getting stuck, or you're not stuck but just haven't ever given me a new video yet for that achievement, then searching for combinations versus permutations or something will get you good videos. So there we go. Questions about the to-do list for week 8. Everyone looks tired and content with the to-do list. Okay. So I assume there's at least one person here who was not here on Monday. And even if that wasn't true, then there's enough jargon that we should probably just go through things all over. So we're in the typicality page and going down to the probability section. We started on Monday with these spinner puzzles. We're not going to repeat that again, but we can do a few other things. And I think what I actually want to do is make a new copy of this page and get some random things at the bottom. Okay. So our first idea was probability versus odds. I'm going to pick a Jamboard page and start listing our jargon. So probability was of all of the possible outcomes, which ones are desired and over which ones are total. Whereas odds It was the desired over undesired. So if we look at the example, what's the probability of rolling a sum of 9 or more on 2 dice? So how many ways could I get 9 or more? Let's make that a highlight. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what is 10 divided by 36? It is about 28%. 10 divided by 36 is 0.27777, so I'll round it to 28%. Check on your own calculator. Make sure that you could do this if it was homework. For the odds, then it is still 10 of them count as what we're talking about, getting a sum of 9 or more, what we are calling the desired outcomes, even if we don't actually care. But now the denominator is the ones that are not shaded in. So if there's 36 total, then it's going to be 26 that we haven't shaded, 36 minus 10. And normally we write this as 10 to 26 with a colon, or 10 to 26 with the word 2, depending on if we're taking the SAT or betting on horses or what we're doing. Another difference is that for odds, it's traditional to reduce our fraction. So we actually should say 5 to 13 or 5 to 13, whereas for probabilities, we don't. So that's that one, and that's that. So my whirlwind review of probability versus odds. Review if you were here Monday. Hopefully I didn't lose you going this fast if you were not here Monday. Again, probability, the ratio of desirable ones to total. And then odds was the ratio of desirable ones to undesirable ones. Anyone want to do more of these before we go on? Okay. Then we had outcomes versus events. And I confess I will sometimes speak incorrectly because I am not used to it being a formal thing. So, oops. So the specific ways the situation can happen are the outcomes, like I roll a 6 and a 2, which would be different than rolling a 2 and a 6. But the collection of outcomes we group together is called the event. So my sum is 8 is the event, and there's lots of different little ways that could happen. We talked about simple events. If I'm trying to roll a 12, there's only one way that could happen with double sixes. That would be a simple event. Or there's compound events. If I'm trying to roll a 7 or a 10, there's lots of ways I could make that happen. So those would be called compound events. And all the events is named the sample space. So this whole chart with all 36 possible options, outcomes is the sample space. We call the events complementary if they both fill up the sample space. There's nothing else that could happen, and they are mutually exclusive. So I roll an odd number or I roll an even number. There aren't other options, and everything is one or the other. Independent events are ones that don't have any predictive effect on each other. So what I roll on one die and what I roll on the second die are independent. Events that are not independent are called conditional. And our example of that was different positive and negative results at a home pregnancy test, that whether or not you actually are pregnant affects the likelihood the test will say different things. Some events happen only when another event happens, and that was called contingent. Those tend to not be exciting for math. So all of those words, let's write them down. Complementary, simple compound, complementary, independent, and conditional. So something simple was, for example, rolling a 2. That could only happen with snake eyes. Something that's compound, for example, was rolling a 3. There's 2 different ways to do that. Okay, again, annoyingly fast. If you were not here Monday, ask me if you have questions, but hopefully okay review if you were here Monday and just needed all these words in your brain again. Anyone want me to talk about these more? Okay. Then we talked about if there were outcomes with replacement or without. If you pick a card out of a deck and then put it back and reshuffle before you pick out a second card, that is called with replacement. And then if you leave that card on the table and turn over a second one, we'd say that's without replacement. We'll worry about that if we actually get to an example, but I can't think of that. Then we started the types of arrangements. And I'm going to skip talking about the toddler books and go to this wonderful table, which will be our focus for most of the rest of class. So if I want to have a bunch of things, and let's start by talking about this one. Oh, no, let's start over here, actually. I have to do them in order. So a complete permutation was the first of our 4 different things to talk about. And it is where you have n different things and you use all of them. So I have 5 books, I'm putting them all on my bookshelf and the order matters. I have 7 people and I am putting them all in a line and the order matters because the ice cream truck might run out of the best stuff before we get to the back of the line. So anything like that, I'm using all of so many different things. How many ways can I do that? So let's use 5. Put 5 items in order. How many arrangements were there? And this is what we did talking about the toddler books before. So we could have 5 ways to put the first thing down, whether it's a book on a shelf or which of 5 kids gets to be first in line. Now there's not 5 options anymore because one person is already standing there. One book is already on the shelf. So next we're going to multiply by 1 less. There's only 4 choices to make for who puts second. And then there'll be only 3 choices left for who's third. And then there's only 2 choices left for who's fourth. And then at the end, there's only 1 person and there's no choices at all. They just are put at the end, or 1 book left. It's just stuck on the shelf. So we could multiply all that together. So 20, 60, 120. And again, this is we're putting all 5 things in our arrangement. This happens enough that rather than write this all out, people just use the shorthand called factorial, which is an exclamation point, and say 5 factorial is 120. So that's this column of the chart. We're talking about a situation that we name a complete permutation. Permutation means the order matters. Complete because we use all of the items. And the way to write how many ways we can do that is called a factorial. And it's just this pattern, the number times 1 less times 1 less until we get to 1. On your calculator, you can do this in several ways. If you have the website one, you can just take a number and put an exclamation point after it, and there you go. There's a secret function button. So I could also type this as 5 and put my exclamation point with a button. I'm not sure why that's any easier than typing it, but maybe you're using your mouse because you're busy, I don't know, drinking with a cup of coffee or something. So there you go. You can click it instead of having to hit that. If you have a different calculator, then there's probably a factorial button somewhere. So on this calculator, if I look carefully, then it is right there. If you are using a, did I close it? I must have closed it. Okay. If we're using our spreadsheet, then you can just type equals fact, and it will give you that. So lots of different ways to do this. Should we do another example problem with complete permutations? No. Okay, start with the number of things, multiply by one less until you get to one. I will do more than one example of the future things because they do get a little more complicated. Okay, next we're going to talk about partial permutations. This is still a review, but I will slow down because it's getting tricky. Now we are not finishing putting people in line or putting books on the shelves. We still have n things and the order matters, but we're only going to use a few of them. And by tradition, the letter we use to say how many of those is R. R is going to be less than n because we're not using all of the n things. How many arrangements can we make? Well, not as many because we're stopping early. So if we're putting all 5 items in order, now let's just put 3 of them instead of all of them. So how many ways can I pick the first thing to put in line or on the shelf or something like that?
Would you start with 3 since you're only doing 3 of them?
But I have 5 in my hand, or I have 5 antsy kids and waiting to be put in line.
The first thing would be 5 factorial.
So I have 5 choices because I haven't used up any yet. They're all bouncing about. Then I have 4 to choose from, and then I have 3 to choose from, and then I stop. So what I really want to do is 5 times 4 times 3 and stop. That doesn't make a good formula though. That's easy to describe. Start with how many things are in your total group, multiply by 1 less that many times. It works as a description, but it doesn't really work very well as a formula. So what we are going to actually do is too much math. We're going to go all the way down times 2 times 1 with 5 factorial like before, and then we're going to undo it. And we're going to divide by the 2 times 1. And then those will cancel out and we have what we want. So what we had on top was 5 factorial, and what we had on bottom was 2 factorial, which is 5 minus 3. By doing n minus r, we're saying keep 3 of these and get rid of the rest. So if it helps to write this formula as n factorial over n minus r, all in parentheses, factorial, you can write it as a fraction. Its name is n permute r. If you have a calculator, it might be a calculator button. Now I can see it. No. It's not letting me put the box again.
David, is that the same as my button, which reads NCR?
Yep.
Okay.
Except no, P, not a C though. Capital P. Find the one with a capital P. And PNR is one way to write it, or NP, whoops, wrong slide, or NPR with subscripts is how some people write it. It's hard to make it look like subscripts when I'm handwriting. Your calculator might have any of that stuff going on. If you are in the Desmos calculator and you wanted to find 5 permute 3, then you could just go right here and say 5, 3 and get the 60. We never actually made it say 60, did we? I should finish my problem. Anyway, so you can use the formula there. You can use the button on their calculator. You could write it as 5 factorial divided by 5 minus 3 is 2 factorial and get the same. So lots of ways to do this. It is not important that on a test you would actually multiply all those numbers with just the multiplication key. If you were using a spreadsheet, then instead of fact, we would use permut, right? 5, 3 and get our 60. So spreadsheets have their own thing too. Okay, let's do another of these. Let's make some bigger numbers. So now we have a whole school, maybe 250 kids, and they have some sort of, I don't know, jogathon or something, and an order arrangement of 5 of them. So first place through 5th place with 250 contestants. So we could write this as 250 P5, 250 permute 5. We could write it as P of 250 comma 5. Those are just shorthand. What we're really doing is 250 factorial divided by 5 factorial. And we get some giant number. I'm tempted to redo my problem so I can actually write my answer down better. What if we have 150? No, even 150 is a lot. Okay, 50 kids, sorry. I want to be able to write my answer down. So what was that? 254 million, 251,000, 200.
Which column are we in? Ordered.
We are still doing ordered items using only a few of them. So factorial of all of the total collection, the 50 in this case, divided by the factorial of how many we're picking out before we stop.
But if it's
oh no, I forgot. It's a subtraction. It's a subtraction.
yeah, if it's n minus r, so
N minus r.
50,
Yes.
it's 50 over factorial 45.
Yeah. Let me go back to the 250 because it will work. No, it won't. It will not work. So it's 50 over 45. You are right. Okay, so it's still the same answer. I just wrote that part wrong. Thank you for catching it. 254, 251, 200. So we're going 50 times 49 times 48 times 47 times 46, and then we're stopping. Let's check that that's the same. Yep. Okay, sorry for the mess up. Questions about this one? I can even add a note to remind myself to do better. So 50 minus 5 is 45.
David, could you do another example of that?
Sure. How many items are in our group total? Just pick a number, Marjorie.
40. Or should we go bigger?
We can go bigger, but then they should be closer together. Because as you saw, even multiplying together only 5 things got really big if they were big numbers.
Okay, let's stick with 40.
Okay, so we have 40 contestants and only 2 winners. And the order matters. Or I have 40 different flavors of Jelly Bellies. I'm picking 2 of them out to eat as I leave the house, and the order matters because the aftertaste will be mostly the second one or something like that. Right? Any group of those 40 things, we're picking 2 and the order matters. So we could write this as 40 permute 2 or permute 42. It's going to be 40 factorial over 38 factorial, because 40 minus 2 is 38. So that's going to be 40 times 39. I could write it as, let's permute 42. I could write it as 40 factorial divided by 38 factorial, or I could write it as 40 times 39. They're all going to be the same way of writing that. We get 1560.
On a calculator, if I'm going to use that NPR button,
Mhm.
what exactly do I type in? I do the NPR and then 40.
I think you go 40 and then that button and then 2 and then equals.
Yes, thank you.
So again, this is the partial permutations. The order matters, so it's a permutation. And it's partial because we're only using a few of the things. Okay, that's as far as we got Monday. So now let's talk about the other side of the chart. In the lecture notes, the complete permutation, different examples of factorial, a nice block quote where we defined factorial, and an example problem for you. The partial permutation, we were pretending that you put 2 books on a shelf and then eat the rest. So you only have 2 of them. And I couldn't on a web page write as nice as before, but when I'm trying to have the end of the factorial sequences cancel out, then the best I can do on a web page is that colored stuff. But I'm trying to write on the web page what's happening right here when I have the colored stuff happening. That's highlight there. So now we're at combinations. I think I want to make this bigger. Okay. An unordered arrangement of some items is called a combination. And it's okay if you don't like that. The example above has what most people would call a combination lock. And the order does matter on a combination lock. So the fact that we're using the word combination is a math jargon, not a real life issue. So if it seems wrong, that's okay. Your brain is right. But we're using the word combination because that's what math people do. They had to think of something other than permutation. Maybe they should have invented a new word, but they just used this one. So think of a raffle where there's 3 identical prizes. It doesn't matter who's first, second, or third. Some other literature uses binomial coefficient. You can click on that link and find out why, but we're not worried about that. When we moved from complete to partial permutations, we had to cross off or cancel out some of the possible arrangements. That's what this crossing out right here was, right? We didn't care about what happens with the last 2 options. Those didn't count as new things. So when we only consider the first 2 letters, right and the town of Reet are the same. Now we'll do that even more. Because we can rearrange things even more, then Wright and Urti, whatever that might be, are the same. Does that make sense? They all have 4 different things. The order doesn't matter. If I somehow was reading words using this type of thinking, order doesn't matter. This word would be the same as that word. So we need to cancel out from our list of possible arrangements the ones that are just mixing things up. But we've already found that answer. There are R factorial ways to put on the shelf R different things. So we take our answer that we had before, this n factorial divided by n minus r factorial, and we divide it again by r factorial. So to be extra clear, many texts, including this website, but not, by the way, our online book, will switch letters. Instead of R, they'll use K. And that's just a kind of politeness. They're trying to remind you we're doing combinations instead of permutations. So for the how many we will pick at a time, they will switch which letters. So you get NCK or CNK, or sometimes they just write it an N over K inside parentheses like that. But all it is what we had before, the big factorial minus the subtraction factorial. But now again, we divide by the little factorial, because that's the number of ways you could just take whatever, the 4 ones we used, and rearrange them. So let's do an example of that. So now we have $50 kids. And what did we have before? 5 winners. Yeah, an unordered arrangement of 5. So we're going to take the 50 factorial, and we're going to divide it by that 45 factorial, because 45 is 50 minus 5. And then we keep going, and we divide it again by the 5. This is the combinations, where we're using K items out of N. We could write this as 50 choose 5, or 50 choose 5 this way. If we're using our calculator, we could do NCR of 50, 5. We could do 50 factorial divided by 45 factorial, and then have all of that and divide it by the 5 factorial. $2,118,760. 118,000. So quite a bit smaller than
So
our
David,
other answer
on that
we had before.
formula for our notes, we need to have that exclamation point after 5. Is that right? It's not
Yes.
not divided by 5. It's yeah.
Not divided by, it's about 5 factorial. Thank you for correcting me again. Too many things in my brain. And if I'm on a spreadsheet, then I can write combin of 55 and get that answer. Okay, let's do more. Everyone ready to move to a new example? We also had 40 with 2 winners. So we could write this as 40 choose 2 or 40 choose 2 with that kind of thing. We're going to do 40 factorial divided by 38 factorial. And then I'm going to just keep going so I don't mess up again. Divided by the 2 factorial. And then I will write that 40 minus 2 equals 38. If I'm using a fancy calculator, now I can use the NCR button. Or I could say that it is 40 factorial divided by 38 factorial. And then all of that divided by 2 factorial. In any case, it's 780. Did I do a screenshot of the calculator last time? No, I did not. Let me grab that. Okay, our last column is boring. If I have 40 things and I want to put them all on my shelf and I don't care what order they're in, I do it and I'm done. And that's it. There's nothing to think about. Since the order doesn't matter, if I'm using them all up, either I finished my chore or I am still singing Spoonful of Sugar. So this is not really an interesting math thing, right? We're putting them all on the shelf and we're done. Ta-da! We are not picky how we did it. We go to the party, everyone gets your hand stamped. Ta-da! Right? There's no math to ask about it. So there's really only 3 things, even though the table to be symmetric has 4. There is one more thing to think about, though. In all of these, everything on this table, let me grab this again. This table is about what we called arrangements, which was the official math word for we do not get to have repetition. Once I put some book on the shelf, it stays there. Once we put some kid in line at the ice cream truck, they stay there. You're not allowed to be in two places at once in the line. You're not allowed to like get dibs on two places on the bookshelf. So the other thing is called a word. And for words, think of license plates. Because license plates don't actually have to have sensible words. It's just bunches of letters stuck together. So if I want to say, how many words can I make with so many letters? How many different ways can I pick the first character?
$26.
26, right? And the second character is again all 26. It's okay if I repeat things. They're not going down by one anymore. And the third one is also 26. And we know what the shortcut is for this. This is 26 cubed. So since we already have a shortcut way to write this kind of thing, we don't really need to worry about it much. This will happen sometimes in the homework. How many different ways could you make a block combination with the numbers 0 through 9 if you were allowed to have repetition? 10 times 10 times 10 times 10, depending on how many digits are in your lock combination, you would keep going. But this isn't terribly exciting. You've been multiplying with exponents for a lot of your math history. It does still show up in the lecture notes. So again, cleaning things up is trivial, and words are the name we call it if you're allowed to have repetition. Okay, questions on any of this? We've done lots of different things, and it's only 3 o'clock.
Yeah, I have a question about the partial permutations that you did. So with the example that you and I worked on, I get the 48 minus 2 equals 38, and that's where you, because you're using a 2 is a partial of 3, but then you've got 40 times 39.
Right, that's because I had a times 38, a times 37, all the way down to times 1. And it canceled out with the 38 factorial, which was also 38 times 37. So
Okay, got it. And you, yeah, and you walked us through that in the first example. Okay, cool. Thank you.
I'm doing that just to show you that they're not often a complicated math problem. This is just 40 times 39 written in a really confusing way.
But we wouldn't want to really use that day to day because it would get super confusing then if we did a 40 factorial over 20 factorial, right? Because then we would be writing out tons and tons of numbers.
Numbers, right. The advantage with the shortcuts, even if they make some simple things needlessly complicated, is that they're just the same buttons to push on your calculator or spreadsheet every time. During the study group, we did first, let me go back to the beginning of our 5A. In an 18-team league, how many ways can the 8 teams for the finals be decided? And we're assuming that it doesn't matter which teams are playing each other first in the eliminations. It's just how many ways do you get 8 with order not mattering. So that was a combination. The order doesn't matter, so it's a C, not a P. You would take the 18, divide it by 18 minus 8 is 10, and then divide it again by the 8. So we talked about that and how the 10 factorial is canceling out. So that kind of thing. In our spreadsheet, we actually have a new tab at the bottom, a new page called probability where we did this. We also actually earlier did problems 2 and 3. So these are words. How many different car plates could be made if we had 4 letters and 2 numbers? So that was 26 times 26 times 26 times 26 for the 4 letters, not decreasing, because it's okay to have all A's. Replacement is fine. And then 2 numbers is 10 times 10. So when you multiply all those together, we got a great big number. What if repetition is not allowed? I need to make this a little wider or something. Then it would go down 26 times 25 times 24 times 23. And after you used 1 digit, you couldn't use that number again. There'd only be 9 choices. And when we multiply all those together, we get something smaller. If you put restrictions on, there aren't as many ways to do it. If you don't like watching the spreadsheet solve it, then at the bottom of the answer key, you could see how someone wrote out number 2 and number 3 by hand. Then in our spreadsheet, we pasted this table to look about things and did 5A and B, 18, pick 8. And you could do it as factorials divided by each other or using the combin or permute phrases. And we also did it out on the calculator all these times, which I should paste in there, right? Oh, that's big. So anyway, if you were here at the office hour, then we did similar things. Okay, I can finally clean all of that up. Now we get to the part that could be genuinely confusing. We'll keep trying to go slow. And we're doing arithmetic with probability. When you do arithmetic with numbers, your basic things are plus, minus, times, and divide. When you do arithmetic with probabilities, the basic things are and or. I can ask questions like, what's the chance I draw a king and a red card? Or what's the chance I draw a king or a red card? So those are the kinds of things that stick together probabilities. And so that's the first adjustment mentally to make, that and or work like plus, minus, times, and divide. They are our operations that we use to squish together probabilities. Playing cards are the traditional way to talk about it, but the problem with playing cards is they have big numbers. There's these 52s all over the place, or 51 or 50 if you start doing things without replacement. So we're going to use the spaceship explosion game. And I need to shrink that a little bit so I can fit it on my Jamboard. Shrink it more. There we go.
I made mine. So I could play. It was fun.
Okay, so now I can make things bigger again. We can use this to think of some different probability questions. The rules of the game where you roll the dice. If you get a spaceship on your result, then you get one more spaceship in your fleet. If you get an explosion, your other person you're playing with, it's a two-player game, loses a spaceship. And if you get a bomb, they will lose a spaceship, but it doesn't happen immediately. So if you need me to go over this more, I will, but we had an email sent out earlier. And hopefully you can look at this unfolded thing and picture the die with 6 sides. So here's our first example. The chance to roll a ship is 1/2, it says. Can I make that bigger? So is that really true? The chance to roll a ship. Well, we have 1, 2, 3. So chance for a ship. So 3 out of 6, which is 1/2. The chance for an explosion, 1, 2, 3. Is also 3 out of 6 it can happen. But it's not true that the chance to roll a ship or an explosion is 1/2 plus 1/2 is 1. Why not?
Do we multiply add the top numbers and then add the bottom numbers independently? So it would end up being 2 over 4.
No. We do have one side of the die that I'm writing on where nothing happens here. So we don't always get a ship or an explosion because we could have this nothing happens side happen. So I can't just write that the chance of ship or explosion, oops, that's not an R, is the chance of ship plus chance of explosion. Which part of the die is causing problems?
The blank spot is causing problems. Do we do 1/2 plus 1/2 and then subtract 1/6?
We do. Tell me why.
Well, 1/2 plus 1/2 gives us the probabilities of those two options, but then we need to factor in that there is also an extra 1/6 probability that nothing's going to happen.
It's not really an extra 1/6. That sounds like there's 7/6. There's one of the die faces that's even more of a problem than the blank one. The blank one just sort of reveals there is a problem, but that doesn't cause the problem.
I get it. It's the explosion because the explosion doesn't happen immediately.
It's not, no, it's not the bomb. We're not asking about bombs at
Okay.
all.
Is it the extra spaceship?
You're on the right track. What do you mean by
Because-
the extra spaceship?
Well, because it's throwing things off a little bit. So you've got the possibility of one explosion. You've got one possibility, another two possibilities, three, and then you've got three possibilities, and then you've got two of the same possibilities.
Let me rephrase what you said, I think.
Okay.
So this square right here is our problem. That side of the die.
Oh, okay. No, I was thinking that because we had two squares that were both spaceships, that it was leaning too heavily in that direction. So, okay.
That just means it's a likely thing.
Okay.
So why does the blue square mess us up?
Is it because the question is asking for spaceship or explosion? And that one has both.
It has both. It's double counting. Right? If we only care about one or the other, then after we've counted that blue side, we shouldn't count it again. It appears here in the half that are spaceships, and it also is being double counted here in the half that have explosions. So if we were to look at all of the sides that work, there's 5 that work, not 6. We're double counting this one. So we need to subtract the overlap. That's double counting. So Eli was correct a bit ago that we're taking away a 6, but it's not that we're taking away this 6. It's that we're taking away this one because we counted it twice. Once when looking at spaceships and again when looking at explosions. So that is our rule of math with OR. Remember, OR is like plus or minus. It's how we stick together probabilities. And the rule is that you add up everything, but then when you're done, you have to check if there's any overlap. And if there is, get rid of it because you've made things too big. So let's write that nicely. The probability of A or B happening is the probability of A plus the probability of B. And then, that's a silly B, we have to say, remember, subtract the overlap. If we're looking at what's the chance of drawing a red card out of a deck or an ace. Well, two of the aces are also red, so we need to remove those two. Otherwise, we'd be counting them twice. How about and? So we'll take this again. Now, one of the rules of the game was if you roll an explosion, you get to roll again. So the chance to roll at least 2 explosions, well, I could get 1 explosion 3 out of 6 times. And then I could keep rolling. And if the chance to get at least 2 explosions would have another 3 out of 6. What am I doing with these numbers? Adding, subtracting, multiplying, or dividing?
Multiplying.
Multiplying. So what we're saying out loud is that 3/6 of the time we rolled 1. Actually, I'm going to change my words here. I'm going to make this reverse chronological order because that makes it better in English. So we rolled an explosion and could roll again 3/6 of the time. Another 3/6 of that, we got a second explosion. So this is a little awkward because normally we like to write things in order, what happens first and what happens second, which is why I did that initially. But it will help you if you get used to, for these problems with and, to think about things in reverse chronological order. That first we had to earn continuing. We had to earn not being disqualified. And then a certain chance of that, we keep going. So the more recent things happen before the word of. And that's how probabilities with and work. So what is the chance that I pick a red jelly bean and a yellow one? It's the chance of getting a red one, because if I don't, then I can't do red and yellow. And then once I have the chance that I got the red one and we're actually doing what I'm talking about, then we can think about the chance of the yellow one also. For these examples, the order we're doing things matters, because you have to sort of qualify first and then keep going. It can be a little more complicated. Actually, not really, but we'll just think carefully. So what if the problem instead says, how can you get all three outcomes only once? So we need to get a bomb, a ship, and an explosion. This can only happen one way. First, we have to do the bomb and the explosion. Why didn't that work? So that's a 1 out of 6 chance. And once we do that, then a certain amount of that will get to keep going. So we need to get an only a ship. And only a ship, there were 2 out of 6 ways to do that. So a different rule. It's not adding and subtracting the overlap. It's you start with the oldest thing that happened first and then multiply, winnowing down. Are we still actually in this situation, or have we disqualified ourselves? So what did I say before? Probability of A or B happening. Now we'll say, no, let's just use the same slide. So they're not hard rules, they're just new rules. You might not have seen them before if you haven't done a probability class. questions about any of that? I see good study group planning happening. Okay, let's look at our textbook chapter, since you think we're okay. So the textbook chapter explains things differently. It has a lot more example problems than I have time to go over in class. The example problems it explains very well. So if you followed what was happening in the lecture Monday and today, I have full confidence that you can read the textbook and follow along with what is going on. It's a little rough if you start with a textbook, which is why we had something that was more carefully arranged, this very useful table, some smaller thing than a deck of cards with the explosion game to think about ands and ors. But once you've had another way to be introduced to probability, this textbook is nice. So it talks about outcomes and events, a simple event, a sample space. It's talking about probabilities, the number of outcomes minus the other ones. I don't think he ever defines odds. He talks about cards. He talks about complementary events where it's either one or the other, and has this kind of equation, which is just saying the probability of not E is 1 minus the probability of E. Let me take this and translate it for you. I think it will be a good thing to start making a list of translations. So this is what the textbook was using for complementary events. So this one is the probability of not E. It's not the same bar as over a decimal, that means repeating it, is 100% minus the probability of E. Everyone okay with deciphering what was written there? So the textbook is writing things in sort of a more succinct and formal way, but it's exactly the same thing we've talked about before. If there's a 30% chance it will happen, there's a 70% chance that the other stuff would happen. Then he has more examples of things. He talks about independent events. He has a nice example problem. Example 7 is great. Are these things independent or not? And then he has his version of A and B. So the probability that A and B both happen is the chance of one times the chance of another. That's what we just did with multiplying things together. Yes. And then he goes on a little bit and says, if there's ors, we need to subtract the overlap. Because the overlap is the chance that they're both happening at the same time. The chance that the die has both a spaceship and an explosion on it. And later he will get to conditional probability. Some things are dependent on others. And that will allow him to say that if things are dependent on each other, we have to actually get far enough along in the event that they happen. So let's look at these two and formulas. They're both saying the probability of A and B. They both say the probability that the first event really did happen. He writes his in chronological order instead of reverse. So this is the first event, the A event. And then he's multiplying by the probability that the second event happens. And this B/A is a fancy way of writing that B happens assuming A did happen, or knowing that A did happen, or measuring that A did happen.
David, are these going to be compiled into a sheet similar
Yep.
to the financial formulas?
Mm-hmm.
Okay.
But just like it was true that his formulas tended to be not very helpful if you didn't understand them, I want you to understand what's really happening more with words before it's just all the rough letters. Some people love the rough letters. If your brain likes the book's way of writing things, great. But there's just too many letters floating around if you don't know what's happening. So, but I will try and put this on the same page so you can just have one page printed. So it's the same formulas we talked about. He just writes them in this way that works once you're used to it, but is just a little awkwardly condensed until you're used to it. The probability that A and B both happen is first the chance that A actually will happen. And then once we've gotten that far, what's the chance that B would happen, assuming that A did happen? So same thing we talked about, but his are in the other order, which makes it a little harder to replace the times with of in your brain, but not too bad. And lots of things. When you get to the section about Bayes' theorem, feel free to skip that. It's really important for politics and medicine, but it is a little advanced. He's putting it in just because he feels like he has to. So you can skip that part. And then for some reason at the end, he does the counting. How many ways can you have this and that and the other? That's what we did with words. The 26 times 26 times 26 times 26 times 10 times 10. Right? So he does that there. He makes a nice tree. I couldn't fit all of my tree with books in one picture, but he has a good one there. Then he talks about permutations. There's the factorial formula. There's his version of how to write NPR, which is basically the only way to write it, so yay. And then NCR, and permute R versus N choose R. This book doesn't switch to Ks, as I mentioned before. Many books would at this point. And then some more example problems using the permutations and combinations. And at the end, he does the famous birthday problem. If you have a room full of 30 people, what is the probability that there's at least one shared birthday? The answer is bigger than most people would guess. So this is a great thing. It is not like Bayes' theorem. It is not extra difficult. You can follow through example 39 and understand all he says and learn about that. When you get to expected value, that's what we do next week. So now you've seen the textbook way of explaining things as well as my way. Okay, let me put on the screen. When are our study groups? I couldn't quite keep track as all of those good things were going on in Zoom chat. Someone tell me, is there something happening tonight?
Sounds like 10 tonight and 10 a.m. on Sunday.
So Wednesday at 10 a.m. or 10 p.m. Nothing Friday or Saturday, and Sunday at 10 a.m. Okay. Somebody says tomorrow at 10:30. So Thursday, is that an a.m.?
Yeah, that's AM, David.
A.m. Okay,
And Julie and I will be there.
okay. Let's look at your homework. So first part we did was just counting things. How many out of 36? How many out of 36 minus that number? So you have one of those. The problem we did Monday about pregnancy tests, here's something very equivalent, but there's a Lyme disease test. We're not doing any of our fancy stuff with permute K or choose K or things like that. We're just counting things on this chart and finding percentages, the kinds of things we were doing first half of Monday. And another one with a slightly bigger table. This table asks you to look at the difference between and or, but you don't need to actually use any formulas. As long as you count carefully, there's no formulas needed for this whole homework 8A. The short answer question, what is a factorial? Give an example and show how it could be calculated. Hopefully you can all do that by now. But then the tricky part, do some research and find an application for factorials in algebra, trigonometry, or calculus. If you just search for factorial on the internet, the first gazillion things will be what we've done about combinatorics or probability. So put 2 words in your search bar. Put factorial and algebra, or factorial and trigonometry, or factorial and calculus. There are applications in all 3 of those with factorials, but you're not going to find them if you only search for factorial. So if you do put 2 words in, you should find something pretty quick. For the next homework, now we're doing the stuff that actually was on class today, that you can choose from 3 appetizers, 11 entrees, and 4 desserts. How many ways could you make a combination? So is this a n permute R, an n choose K, or is it a word? A pianist wants to play 5 pieces at a recital. In how many ways can the pianist arrange all 5 of those? But the order matters. Or a contest has 175 contestants. How many ways can you award first and second and third that are different? Order is mattering. A local pizza shop is having a 5-topping special. They sell 14 different toppings. So how many ways can you pick 5 out of 14 when order doesn't matter? Because the pizza is going to be the same no matter which order they decorate. The serial number on a dollar bill has a letter, 8 digits, and another letter. How many ways are there if it can't repeat or if it can repeat? 2 kids play a game involving flipping 2 coins and keeping score. They flip the coins one at a time. One kid gets a point when the first coin is heads. The other gets a point when the second coin is heads. And they're surprised when 3 rounds happen without any points. So what's the chance they could have 3 pairs of coin flips with no heads anywhere? A problem I've mentioned out loud several times. You have a normal deck of cards, you shuffle it. What's the chance of getting a red card or less than 5? Some of the less than 5 are also red cards. There's overlap here to get rid of. This one needs a Venn diagram. It's not done yet. A group of athletes has 12 people, 8 men and 4 women. What's the probability that a randomly selected team of 3 people would be either all men or all women? So some of these should be more obvious than others. And as always, try them, talk about them, work together. The short answer question here is less researchy. You don't have to figure out anything yourself. It's just explain the difference between combinations and permutations for given values of, whoops, that should be N and R. N and R. Which is larger, P and R or C and R? N permute R or N choose R? So explain which is bigger and why, and can they ever be the same? And probably the easiest, why are probabilities always between 0 and 1? Why can't we have a negative probability or a probability of 12? So put things in your own words, just double check that you've thought these things through.
David, I was reading number 5 on part B, and I thought I did it right, but I don't think I did it right after I read number 6. Can you show kind of just go over like how we would go about doing that one?
Sure. So we have a letter. So something that's a letter. We have 8 things. And those are all numbers. And then we have one more letter. So we're assuming that we're not allowing repetitions. So how many ways can I put in the first letter?
26.
But now one of those is taken. So for the second time, I have a letter
25.
25. And the first time I pick any digit, 0 through 9.
I guess 1.
So just 10, but then one of those is taken. So I have a 9 options and so on. And then somehow I put all these things together. What will I do with my 10 different numbers?
Multiply them.
Multiply them. So I don't know what that is off the top of my head, but it's a pretty nice big thing. Okay, we don't really have time for a quiz right now with 4 minutes, and you just had a midterm anyway. I had various ideas for quizzes, but nothing really jumped out. Anyone have a good idea for a take-home quiz?
I just ask that you go easy on this.
So, how about another short answer question? Would that be good? This seems to be much more of a organize your brain topic than a can you punch in numbers topic.
I like the idea of a short answer one and like doing a little bit of research, maybe even doing like find a good problem or find a good statistic on like why is it good or something like that.
Okay. Well, that's my homework then, to get you a good short answer. Okay, well, have a good time till Monday. I will do my best to remember that, as always, we do have a Saturday 9 p.m. And if I can, I'll stop by the other study groups, but no promises. So